Hello everyone. In this video we present a demonstration of our Artilians simulator, a simulator for evaluating the performance of cloud native applications. As you can see, the Artilian simulator is open source. It has been released under the MIT license and it's publicly available on GitHub, so it can be downloaded by using the git command. The simulator is mainly written in C++ and can be compiled by using the make command. So what is the Artilian simulator and why did we develop it? It simulates the Artilians framework. Artilians is a set of Kubernetes extensions we proposed in a previous paper for executing real-time and fault-tolerant applications on a Kubernetes cluster. It's based on modeling each application as a directed acyclic graph in which each task can process some inputs and generate some outputs for the next task. And each task is basically a microservice composed of multiple load balanced container instances. So we end up with something like this for a cloud native application. In previous works, we formally analyzed this model, allowing to dimension the number of containers for each task so that we guarantee that the graph can process each request in a maximum time. Unfortunately, this analysis is very pessimistic because it's based on worst-case assumptions. Look at this example. This is a cyber-physical application, a controller for a mobile robot. This controller can be offloaded to a cloud. And in this application, each task is described by the worst-case service time. So we know that the decode transform task can process its input in at most 10 milliseconds. And the analysis is based on these worst-case assumptions, so it will be very pessimistic and will end up over-allocating resources for our task. Here we are interested in a less pessimistic model. For example, we would like to describe the execution times of each task through a probability distribution. Look at, for example, the code transform task. Again, in our original model, it was described as a worst-case service time of 10 milliseconds. Here, in this new probabilistic model, we can describe the probability distribution of the service time. We know that it's possible to serve some input in 10 time units in 10 milliseconds, but this only happens with a probability equal to 0.1, and shorter service times are also possible. Unfortunately, we don't have a formal mathematical analysis for this probabilistic model yet. So what we do is to use our simulator for simulating these cloud-native applications based on this probabilistic model. Each application is described through a standard directed acyclic graph described through the graph with syntax, the dot syntax. Each node has some attributes, for example, the distribution of the execution times or the number of container instances used to implement this microservice. Notice that in this initial simple setup, we assigned the same number of container instances to each microservice. And this results in a very bad performance and resource waste. So the simulator can parse this description and simulate the application and generate for example, distribution of the response times. And you can see that the graph response time in the worst case is 116 milliseconds. And For example, to serve, we have a probability of about 87.7% to serve a request in 60 time units. The simulator also tells us that the code transform task, for example, is implemented by two containers, and each one of these two containers is busy for about 60% of the time. So these containers are underutilized. Maybe we can use one single container for this task. On the other hand, the tag position task is composed of two containers which are much more loaded. They are busy for 75% of the time, and this is why the response times of the graph are so high. So we can increase the number of container instances for this task. And we actually rewrite a configuration for this example, reducing the number of container instances for some underutilized tasks and increasing the number of container instances for the tag position task, which was much loaded. And we can simulate again. You see, when we start the simulator, we can ask to use a deterministic pseudo-random number generator so that the simulation is exactly reproducible, and we can specify the seed. Then we can also specify the length of the simulation. And if we simulate this new allocation, you see the worst case response time of the graph is much lower, and the probability to serve a request in 60 time units is increased to about 99.8%. The simulator is, of course, much more complex than this, can simulate more things. For example, we can simulate failures in the containers. We can say that a container has a 3% probability of failing after processing its data, or can fail during the processing, or can fail in various ways. And we can also add a timeout for resending a request after a number of time units if the request has not been processed yet. So this is useful when we have some failures. If you are curious to see what this simulator can do and how it can be useful, please come to our demonstration and see it. Thanks.